So today we have Menachem Lazar from Bar-Ilan University, who will be speaking to us about high-dimensional data, level set geometry, and Voronoi analysis of spatial point sets.
All right, thanks for having me. It's wonderful to be here. Thank you also for your special accommodations for my scheduling constraints. I usually teach on Wednesdays, so yeah, thanks for tuning in on a Tuesday. Okay, so today I'd like to tell you about some work of mine that concerns, well, I guess you could see the title, data, level sets, Voronoi cells. The project starts with a very particular problem. It's more of an engineering problem, so it might, if it doesn't feel very mathematical, then that means you're following along great. But what I'd like to show is that this very engineering-focused problem and some of the solutions which have been proposed and which people have used, both the approaches and their limitations, I think, are best understood in context of a more mathematical approach. So what I'll try to do is spend some time describing the engineering approach. In some sense, it's very simple. I think if you guys have, small children, they can probably, I think, understand that part too. And then try to highlight that mathematical aspect and show why this is really cool. Oops, sorry. Okay, so the problem. This is a picture of a computer that I assume many of you are using as you're watching this. And computers are made, their case at least, of this one is made out of metals. Okay, and if you look at a piece of metal, if you look really closely at your computer, maybe under a microscope, you'll see something that looks like this. Okay, so on the bottom left of the screen, you see some assortment of these different regions, different colors. Each region is called a crystal for reasons that will become clear in a moment. And the set of all of these together is called a polycrystal, many crystals. Okay, so if you zoom even further, and you can't use you need a heavy-duty, expensive microscope to do this, you'll see something that looks like this. Okay, so this is just the results of the simulation. I'll make this picture bigger. 1 second. Okay, there we go. Okay, so this is a picture of what's called a polycrystal. And I want you guys to pay attention to two things. One is these circles, each of which is meant to represent an atom. Most of the circles are ordered really nicely. Start with any atom, and more or less the atoms lie along nice lines, actually 3 nice lines in 3 different directions. And that describes most of them, but there are regions where things are less nice. Maybe on the bottom left, you can see that they're also nice, but maybe the orientation of those lines is different below in the bottom left than it is in some other areas. And it's probably a little bit hard to see this, and it's supposed to be hard. Okay, so what I'm going to do is, okay, so I colored it to help make it a little bit clearer what I meant. And if you look at the yellow regions, those are the crystals. You could think of them as lattices or physical approximations of lattices. They're like the Z2 lattice or some transformation of it. But aside from the crystals, you see regions between crystals, boundaries between them. And even in the interior of the crystals, you see what are called defects. Okay, so I won't say much precise about them, but on the left side, you see this ring of red and blue colored circles. And in the middle of them, there's like a hole. The material scientists call this a vacancy because there's a vacancy in that space, and there's an atom missing. Somewhere towards the middle, there's like 1 red and 1 blue circle next to each other that they call dislocation. The ideas behind it are a little bit more complicated. And then these like one-dimensional lines of defects are usually called grain boundaries. Okay, yeah, and now the reason that all these things are interesting to them is because first of all, they're found in all materials, or basically all metals. Every piece of metal that you've, or almost every piece of metal you've ever touched, your computer, your keys, your car, and so forth. If you look close enough, look something like this, and they have all these sorts of defects in them. And number two, these defects, to a large extent, determine properties of these materials. If you imagine pulling apart the sample and you want to know where will it rip, you might guess more or less correctly that it's most likely to rip along these lines, the red and blue lines. Okay. If electricity is passing through it, you might imagine that it would pass through it as nicely as possible if the system in some sense was as nicely organized as possible, and somehow these defects, these boundaries between the crystals, and otherwise somehow impede the travel of electricity. Okay, so these things are true. They're important. They're interesting, and the material scientists, really want to understand, given a material, how many defects are there? What kinds of defects are there? How does the creation of this material generate certain defects? How can we control the defects? And so forth. And that would allow us, at least in theory, to develop superior materials, metals, and other crystalline materials. Okay. Now, even to do experiments of this sort in a lab is expensive, is laborious. So what a lot of the scientists do, computational material scientists and computational physicists, they'll use big computers to simulate these systems. So they might use what's called molecular dynamics. They'll solve Newton's equations of motions for all the particles, and they'll heat the system and whatever that means in a certain way, and see what happens. How do the defects propagate? If you apply a certain stress to the system, what happens? Can you make them disappear? Okay, so the computer might have, this sample has several hundreds of atoms, but maybe there's several thousands or millions or even billions of atoms in these simulations. And if you want to be able to sort of analyze the systems, you don't want to sit and look at these atoms one with your eye. You want the computer to be able to do that. Okay, but the problem is the computer doesn't see this; it sees this, or more likely this. Okay, so the computer just sees lots of numbers, and it doesn't, necessarily have some way of seeing what we want it to see. Okay, and so the problem is, this is what I told you, what I promised is a very engineering focused problem, is how can we identify defects? Okay, given, let's say, lots of coordinates, how can we find where the vacancies are, where the boundaries between the crystals lie? Okay, now, again, for the mathematical, either inclined or the mathematical part of you, you're probably complaining and annoyed because I didn't really tell you what these defects are. I didn't define them. I didn't say anything precise about them. So if you can sort of hold that in and follow along anyways, I'll appreciate it. In part, we have this problem because there's a problem, but I'll say more about that later. Okay, but it's not because I forgot to stick the definition, that you expect in a typical math talk. It's because there isn't really a definition. But okay, but hopefully there's still interesting things we could say about this even without an actual definition. Okay, so how do the engineers do it? Because they don't care about maybe the definition. Okay, so they have this data, and what they're trying to do is see this. And I mean, what essentially they're trying to do is they're trying to look at every particle in the system represented by this red particle, look in some neighborhood around it, the blue particles, and then say something about it. Somehow characterize it. Are the neighbors nicely ordered? If they are nicely ordered around it, are they in some crystal, some lattice fashion? Are they, something else? So what they do is they develop all sorts of what they call order parameters, which are essentially functions that try to capture the order nearby. Bond angle analysis, I wrote. I'll explain some of these a little bit. Coordination analysis. Maybe they count how many neighbors are, within a certain distance away. Central symmetry analysis. I'll explain that a little bit. Neighbor distance analysis. So they sort of do what you and I would do if someone said, "Here's a bunch of data, look at it and try to do it." And they think and and I'm not saying there's no good reasons why they make up these order parameters, but in some sense, it's an engineering problem. You have the data, you're trying to analyze it, figure something out, and this is what I meant. Asking a kid, they can start looking at it and say, well, let's compute something. And maybe something decent would come out. Okay, so here are two ideas, conventional methods. You have a particle in a perfect crystal, the red one, and you notice that it has 6 neighbors that are close by or equidistant. And I mean, since this is a picture of a lattice, a picture of a piece of a lattice, you notice that every pair of neighbors, the neighbors come in pairs. Right? I mean, if it's a lattice, then if you add some displacement vector in one direction, you should get a particle in the opposite direction. And so you could look at whether these particles, these neighbors, actually come in pairs or not. Or you might notice that the angles between the neighbors, we need to make this precise, but let's say we can, that they're all, let's say, the same. Here, they're all 60 degrees. Okay. Or you might notice that, well, they're all 60 degrees, so the variance or the sample variance of those neighboring angles should always be 0, right? Because the variance of pi over 3, 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 pi over 3 is 0. And then you say, well, when we look at real data, okay, that's supposed to be real data, more real data, not actually real data, but you say, oh, maybe the neighbors aren't actually now in pairs because even these quote unquote opposite neighbors, they don't exactly cancel out these vectors. The angles maybe are not exactly all 60 degrees, so the variance now is some positive number. And the idea would be, well, maybe the smaller that variance in the angles, the more crystal-like it is, and higher it is, maybe we should say, well, I guess we must be nearby a defect. Okay, so that's one idea. And here is an application of one of these engineering methods. So the figures until now are mostly 2-dimensional. I'll use occasionally a few figures from 3-dimensional systems. So this is data from a simulation with maybe there were 5 million atoms, maybe 7 million atoms, of a 3-dimensional piece of nickel heated to 85% of the melting temperature. This all simulated in some big computers that could run these molecular dynamics simulations. And you can sort of see that they come in regions, in these crystals. The different regions of this picture are ordered differently. And what I'm going to do, I'm going to color all the atoms according to one of those order parameters. There you go. Okay, so this is the polycrystal, the many crystals where every atom now is colored according to the variance of the angles or something like that. Central symmetry, so it has to do with how those neighboring atoms come in pairs or not. Okay, and I didn't put a key here, but the bluer the particle it is, the closer to 0 that some number is, and the more crystal-like it is. And that means that the particles that are dark blue in some sense belong to the interior of a crystal, and the ones that are colored lighter colors, brighter colors, belong to defects of some kind. And again, I never told you what a defect exactly is, so just keep in mind sort of the layperson idea of what a defect is. And you can see more or less where these defects lie. There are boundaries between crystals. Some are perfectly flat, which is sort of cool. So material scientists already know about these things. Some are a little bit rougher. They know about those ones too. But so right now we've just colored everything by some number that we computed, some number between 0 and, I don't know, some high number, maybe, let's say some number in the positive or non-negative real numbers, and some kind of variance. And what we should do is we should choose some cutoff, okay? And we'll say that any atom here that has a value of this order parameter below a certain value is considered like very crystalline-like, and we can sort of ignore it because we're on a hunt to like look at the defect. So what I'm going to do is I'm going to choose some cutoff on the top right, parameter cutoff, and I'm going to erase anything below that cutoff. And I'm going to start tuning this slowly and erase more and more of the atoms until you have like a better picture of this structure, okay? So what you should be seeing, again, rough, undefined, okay? But you see this network of boundaries between these different like cell shapes, these different crystal shapes. And what we try to do more or less is like filter out the actual crystal itself, crystals themselves. And this tells us something, okay? It's not perfect, but it's something. Now, well, one thing we should notice is actually two things having to do with the error. And again, error is not precise, but one is there's certain atoms that appear, like it seems, appear in the bulk of the crystals. And if they're like in the bulk of the crystals, then maybe we shouldn't have colored them, because maybe, yeah, maybe we shouldn't have colored them. Are there actually structural defects in there? Or maybe, and this is part of what's going on in some cases, is these thermal vibrations cause large deviations in these order parameter values. And so maybe what you're seeing is the effect of noise, but not actually what we're interested in. It's not like there's an extra atom somewhere there or a missing atom. Okay, so that's one thing. And then the second issue that comes up is, we have these, let's say, boundaries between adjacent crystals, and we expect to see maybe, or we'd like to see a full boundary between the two crystals. But if we adjust this cutoff parameter like in a bad way, we sort of ended up like leaving out a lot of it. So that's not so good. Okay, so material scientists, the computational kind, have ways of dealing with these things. Sometimes they'll cool a system down before they do the analysis, or they'll take some average over time, which, remember, this is the engineering perspective, so it's okay. It's okay. As long as it works, it works. And that's really all we need. Okay, but what I wanted, but there's still something that if you're the mathematician, you feel like maybe you're missing something. Like maybe we could say something more, or maybe there's like a nicer picture of what's going on. So that's what I want to tell you about. Okay, so that's the second part, where we're going to try to abstract the problem. Okay, and this is what takes us into data reduction and data classification when the data lives in some high-dimensional space. Okay, so what is that high-dimensional space? Okay, so here's where I'm going to start. You have this red particle surrounded by a bunch of blue turquoise particles, and we're interested in communicating. So I want to tell you somehow how those neighbors are arranged. That was what we're trying to do. So one thing I could do, I can look at the displacement vectors that, like, say, the distances or the displacement vectors to all the neighbors, and I could write them all down. Okay, so if I write them all down, in some sense, that gives me all the information of the local neighborhood. So maybe we say we're going to look at the 10 or 100 closest neighbors, and I'm just going to tell you where they're all located relative to that particle. In some sense, this gives you all the information we need. This is, so we could calculate the angles from here, or we could calculate the number of neighbors that are up to some distance away, or the variance in the distances from the nearby neighbors. So everything we could do from all of this data. Okay, but the problem is it's a lot of data. it's almost like I gave you that list of all those bunch of numbers. They don't tell you anything by itself. We want something tractable. At the end of the day, we don't care about all this theory or whatever. We just want to know, is this particle part of the crystal, part of the defect? Okay, so we should, so what we do is we develop those order parameters that I told you about. Now, what I think is useful to do is to think not only about these particular arrangements or about particular order parameters, but think about the space of all arrangements. Okay, so this is the configuration space I want you to think about. Think about all possible ways of arranging, let's say, n nearest neighbors. Okay, I left this as an ordered list, but maybe we'll say we don't really care about the order of the n nearest neighbors, so we'll mod out by the permutations. So have some sort of quotient space. So the space might be a little bit more complicated, but the idea is we have this high-dimensional space. Okay, it's more or less, let's say, 2 times n or 3 times n. So it could be 200 dimensions or 300 dimensions, depending on how many nearest neighbors we look at. But in some sense, this tells us everything we wanted to know. And every point here in the space describes some arrangement of particles. Okay, that point, this is just a schematic. It's not accurate within a certain percent or whatever. Okay, and that point there might describe how those neighbors are arranged. Okay, and here I put a few more, and every point in this configuration space sort of describes how a bunch of neighbors are arranged relative to some central particle. One thing I'll acknowledge, maybe some people will be bothered. There are different numbers of neighbors in each one. It's just a schematic, so we can pretend they're always the same, since I was telling you to look at this space that had exactly a certain number of particles. So I only drew a few, but I mean, the idea is that the arrangement of neighbors relative to particle sort of lives in some space. And on the bottom left now, I sort of perturbed the particles a little bit, the neighbors in this square lattice, and that corresponds in some sense to a perturbation in this configuration space. The same here for these hexagonally packed crystals. Okay, so that's the configuration space. And what we were trying to do before is to somehow classify this data, right? Like, at the end of the day, I don't care about the configuration space. I don't care about some order parameter, whether it's 17 or something else. I want to know, is it crystal-like or not? Is it a certain type of crystal or not? So maybe what we're going to do in this classification, we're going to take all arrangements that are represented by points in this circle in the middle and call them all hexagonal, or all arrangements here and say that is an arrangement of particles in a square lattice. Okay, or anything up there, it's telling us more or less about some defect. So that picture on the top right is supposed to show a particle in a square lattice, but which is missing a neighbor. Okay, that was the vacancy, essentially. Okay, and that's what we'd like to do. We want to classify data with high dimensions, and we want to, at the end of the day, come away with a clear algorithm or way of thinking about what kind of arrangements we have. Okay, but the so we have this configuration space. Somehow we have an order parameter space, which is reducing the dimension of the data, and we want to use that to classify the data. But the problem is, okay, or before we could get to this, we were using these order parameters. So I want to say something about that. Right. So when we start off, we just have tons of numbers, maybe even a configuration space where we can think about, and we have this real valued continuous order parameter. So everything I told you about before, the centrosymmetry and the like looking at the variance, those are continuous functions in the coordinates of these neighbors. Okay, so you can think about these functions as some way of coloring this space. Okay, and And the classification would happen when we, like, maybe we'll choose a cutoff. If you remember those cutoffs that I used when I showed the picture, and you'd say any arrangement of particles that has a central symmetry value of under 0.2 or whatever it was, we should classify as being a crystal. Okay, and something like that. But what ends up happening, and again, this is all schematic, but it's to explain sort of some of the problems we had before. Imagine that instead of looking only at that one area that's close to the middle, we look at some arbitrary level set of the order parameter value. So maybe we pick 0.5. Okay, so I mean, I don't think the curve exactly follows the color to the T, but what you sort of sense, it's a continuous function on some high-dimensional space. Well, in this case, let's say on R2 in the figure, but corresponding to something else, you end up having what's essentially a thin but large set, like the set of all points in configuration space which map to the same order parameter value is thin, in the sense that if you perturb a little bit, you'll get off that curve. But it also, at least in this picture, is large. And the consequences for us are such that on the bottom left, maybe a square lattice has a order parameter value of 0.3, and the perturbation of it, maybe it's also close to 0.3. But if you sort of trace that curve all the way to the right, well, it might indicate a very different type of arrangement of particles. So what you might end up having is these level sets that take points far apart in the configuration space and map them to the same order parameter value. Okay, I know this part might feel a little bit far away from mathematics, so I'm going to actually get to mathematics itself in a second. Okay, so this sort of raises the question. Oh, okay, so this is, sorry, another picture. So we took that configuration space, we colored it by the continuous order parameter value, and again, we have this sort of similar thing, that these two very different arrangements of neighbors are somehow, oops, by mistake, classified the same way. They're both classified as bright green or something, or green something. Okay, so that's not so good. So you might say, like, Menachem, maybe you just chose a bad order parameter value where, or sorry, a bad function where the level sets are all big. Like, ideally what we want to have is some way of breaking up, let's say, the plane in the picture or some higher dimensional configuration space into regions where all of the level sets are small. Like, that would be great, because it means that if two arrangements of particles have the same order parameter value, we know that means they're similar. Like, they're close by in the configuration space. And then if they have different values, I don't know, they could be very far apart. Okay, so this raises a actual mathematical question. I typeset it in computer modern, so everyone would know that it's an actual math question. Okay, so I changed the font. Okay, so here's the math question. Think about it. It's not super complex, but can we construct a continuous function from Rn to R such that the diameters of all the level sets, the inverse images of real numbers, are bounded by some universal constant? Okay, so of course, if n equals 1, so the answer is yes. You can take the identity function, and every level set is just the point. Okay, that's boring, but think about the plane. Are there any continuous functions on the plane where all the level sets are small? Okay, I mean, maybe the intuition is, well, there's no way you could sort of take a big set from R2 and sort of map it to some small set R1 and not have points in R1 that were mapped from some also infinite or big set. Okay, so I don't know. You probably think that it's not possible, and if you think it's not possible, you're right. Okay, so I'll just prove like very easily that if you take any Rn and you have a continuous function on it, then you'll have level sets that are necessarily bigger than any bound. Like if you choose some value m, there'll be level sets that are larger than m. So here's the, I don't know if it's a sketch or maybe it's actually a proof. Yeah, maybe it's a proof, it just is short, so I wrote sketch. But okay, so imagine that you bound all the level sets by some value m, okay? So you make them all small. Let's say you were able to do that. So now choose 3 points that are sort of far apart, more than m apart, let's say 2m apart, and that means that they must all be in different level sets, right? If they're far apart and the level sets are at most size m, they must be different in different level sets. That means their value under this function is different. So it's a real valued function with an f of a, f of b, f of c, and we'll just assume without loss of generality that b is somewhere in the middle. Okay, but we could draw a line or a curve or any curve between a and c, that's where the whole curve itself is far away from b. But if you remember first year calculus or wherever you did calculus, the intermediate value theorem tells us that there's some point x between a and c on the segment, which maps to that value, that same value as b does. But that means that, of course, that x and b are in the same level set. But we know that x and b, we chose them on purpose to be far apart, more than m. So basically, we show that you can't do that. And the upshot for our purposes is that we have this high-dimensional configuration space, and we're using a real valued function on it. We shouldn't be surprised at all that there are level sets, or that there are values of their values under this function, such that the inverse image of that value is some very, very big space. That there are points really far apart in configuration space, and where the data sort of lives. They're very far apart, but which map to the exact same order parameter. And that's sort of bad because it means that if I tell you, I don't know, 0.3, you might know absolutely nothing about where in data space that point lives. Okay, you can't go backwards. That's sort of unfortunate, sort of sad. Okay, so you might say, okay, well, that's sort of bad, and I understand why it's not great, but maybe we were silly. Maybe instead of taking a real value function, we should have gone to a more powerful vector value function. Like maybe instead of mapping our data from Rn to R, well, we'll take a few values of m, okay? And what you'll notice if you think a little bit about it is that the intermediate value theorem doesn't really help you in this case, because you don't have sort of the same, you don't have that theorem in this case. I mean, it's not even clear what it would mean to have a point between the A and the B. But so here's the question: can you take some high-dimensional space and map it down? Maybe you need to have at least a few dimensions, but maybe you could map 100-dimensional space to 3-dimensional space, which would be helpful. It would make, in some sense, your problem a little bit more tractable, and somehow still avoid having these very big, level sets. Okay, can you do that? So hopefully, I mean, there's some hope, but sorry to disappoint you. It turns out that you can't. Okay, so this is a theorem. It's short. It's not deep. It's not complicated. The proof is about as short as the previous one. The idea is to use. I'm sorry I didn't write the details, but the Borsuk-Ulam theorem, for those who know something about it, if you take the unit sphere and you have a continuous function on it, where the dimension of the function, a vector value function on it that's sufficiently low, or it's as low as the space, you end up having these antipodal points that map to the same point. But antipodal points are on the same level set, which means you can essentially make your level sets arbitrarily big. And this is for any case where n is greater than m. So no matter what, you have data, it lives in high-dimensional space. You're trying to make it tractable. I mean, in our case, it has to do with these particle arrangements, but in theory, you have all sorts of data, and you want to classify it. So you're going to try to reduce the dimension of the data, and you're going to end up having, if you use, continuous maps, you're going to end up having this problem, what I call the curse of continuity. Okay, instead of the curse of dimension, the curse of continuity, you're going to end up having points in the space far away that map to the same point, which means you can almost never go backwards, or you have no sort of bound on the error, or no bound on the inverse problem. Okay, so that's sort of not so nice. But you'll say, well, whoever said that we should use continuous mappings? Maybe that was our mistake. Okay. Like maybe if you use the continuous mappings, you'll have this sort of problem, but maybe there's discontinuous mappings that can avoid it, and that's a good intuition, because we can always take the configuration space and break it up here discontinuously. So here what I did is I broke up the whole space into these cubes or hypercubes, m-dimensional hypercubes, and there's, let's say, a different value, like a different color in every one of the cubes. But I think we avoided the problem because let's say the diameter of every cube is square root of m or n or something. Yeah, let's say the square root of n. Let's say that you have unit cubes in n-dimensional space. So the diameter of each one is square root of n. So if you have 2 points that have the same order parameter value, you're guaranteed that they're going to be close even in the configuration space. So that's sort of nice. You might not know exactly where they are in configuration space, but you can always choose a small enough, if you want, a small enough, cubes of small enough, radius or linear dimension, whatever it is, and end up being able to classify let's say classify your data using only one number, maybe the color, 1, 2, 3. So you can even map it to the integers or whatever it is, and end up having sort of a relatively nice way of describing the data. So that's nice. And then I guess I should add one more point here is what's really nice. These level sets. Okay, so the function's not continuous, so we need to be okay with that. But if we could get over that, one of the nice things is that at the end, in general, you start with a point in the configuration space. It's classified as having a certain structure, and then you move it around a little bit, you perturb it, the classification doesn't change. So it's robust in that sense. So if I have a perfect crystal, and each particle corresponds to, let's say, a point in the middle of the green box. So when I perturb the crystal, I heat it up a little bit, I'll more or less stay in that same space. So that's pretty nice. Okay. Oh yeah. Okay. So maybe that region of space, the green one is all these like nice green crystal, and the orange one is like square crystal, and at least we have hope for having some way of classifying or identifying these structures in a robust and useful way. Okay, but this is just a schematic. I didn't describe how I should do it. Is there a good way or worse way of doing it? So this takes us to the solution, what I call Voronoi topology. It's particularly relevant to this type of problem, and I'll get back to the application where we started from. But I'm just going to give you like a brief overview and show how it fits in with what we're doing. So here is an even simpler example than before. If you look on the left side, everything looks really nice. If you look on the right side, everything looks really nice. But you'll notice that somehow between the left and the right, something changed. The orientation of these crystals changed. So there's, I guess, some sort of boundary between them. So what I'm going to do is I'm going to look at the Voronoi tessellation. So I could have put a definition, but I didn't. But the Voronoi tessellation of a bunch of points is some way of partitioning the space into regions closer to one particle or one point or one whatever than to any other. Okay, so here each cell in the picture is the region of space closer to some central atom or particle or point than to any other. And what you could notice or should notice or might want to notice is that on the left side, all the Voronoi cells are hexagons. They're actually nice hexagons, perfect hexagon, regular hexagon. And same on the right. And somewhere in the middle, it looks like some of them have more or fewer than than 6 edges. So I'm going to color them. Okay. So what I did is I colored the particles by the number of edges of their Voronoi cells. And voila. Sorry, I forgot that's like a Hebrew word or Arabic word. I don't know. And lo and behold, you have some way now of identifying, or maybe defining. Well, I'll keep it identifying for now. The boundary between these two crystals. Okay, so here we have some chain of Voronoi cells that don't have 6 edges each. Okay, and that's it. I guess you probably guessed by now. That's essentially what I did before. So I colored all the particles according to the number of edges of their Voronoi cells, and in some sense, you know, it shows something. It sort of shows some of the structure in this system. Okay. Thing is, we have yeah. I said I'd show some 3-dimensional pictures. So here is a 3-dimensional system, and the Voronoi cells are 3-dimensional, I guess, polyhedra instead of polygons, which makes sense. Okay. But here, actually characterizing the Voronoi cells, or what I call the topology of the cells, is a little bit more delicate. Instead of counting the number of faces, which is nice and a way of characterizing them, what I'm going to do, what you should do, the right way of doing it, is not only the number of faces, but understanding what faces the Voronoi cell has and how they're arranged, which is essentially the isomorphism class of the edge graph. So there's some deep theorems from the early 20th century about, that connect the polyhedra to these planar graphs. And what we want to do is we're going to characterize these polyhedra by thinking about them as planar graphs and the isomorphism class, which essentially is a relatively easy problem to do computationally. Isomorphism is hard, but planar graphs is not hard. Okay, so at least it's a practical tool too. Okay, so we can now classify arrangements of particles using, you know, these Voronoi cells and their topology. So that's what we're going to end up when we go back to the configuration space to break it up using this classification. For those of you who remember a class in chemistry you may have taken, or physics in high school or college. So these are special lattices or crystals, body-centered cubic, face-centered cubic, and hexagonal close packed. And these are their Voronoi cells. So I mentioned these 3 in particular. Probably 90% of the metals that you come in contact with have one of these 3 structures: copper, silver, magnesium. I mean, yeah, the list goes on for a long time. Not all of them, but most of them. Okay, so these are the Voronoi cells of these arrangements, these lattices. Okay, but we have a little bit of a problem, or a big problem. Okay, and the problem is that if we use this approach for classifying Voronoi cells, well, sometimes we're going to run into trouble. So here's a square lattice. The Voronoi cells are all squares also. There's this duality to it, to the problem. But if I perturb the atoms a little bit, the Voronoi cells change, like the number of edges, and I mean what they look like, and also the number of edges. Okay, so keep that in mind. The same problem happens in 3 dimensions too. So if I perturb this face-centered cubic, arrangement, the Voronoi cells change and the classification changes. So suddenly you get Voronoi cells with more than 12 faces, 13, 15, 18, anywhere between 12 and 18. So how should we understand this? So the truth is, I sort of fed you a lie. I mean, it wasn't a lie. I didn't explicitly tell you that this, that this was the case, but I showed you a picture like this. And then I said, okay, Voronoi topology, blah, blah, blah. But this is not the right picture. In particular, see that square lattice on the bottom left, that shouldn't be in the middle of a region. It actually sits at the intersection of many regions, or at a point that's in the closure of in this case, 4 cells, or actually 8 if you count the edges, or 9 if you count the place inside too. So you have these certain arrangement of particles. I mean, this is in 2 dimensions, and 3 dimensions you have similar story, where infinitesimal perturbations, or almost all perturbations, will result in changes in the topology. Instead of having that one square in the middle, you could end up in the green, red, blue, or light orange section and have a different classification. But by itself, that's not terrible. I mean, what we could do is just now associate all of those regions, at least in theory, with a square crystal, with a square lattice. Okay, in 3 dimensions, these there's some arrangements. The body-centered cubic that I have in the middle is stable. That is, it could, if you move it, it won't change the topology, the combinatorics of the Voronoi cells, but these other 2 will. Okay, and it turns out that actually, if you perturb it, you have many possible resolutions. Here are 3 of them. It turns out that there are thousands of them in these special systems. 6,000, 20,000. It's not, yeah. So there are many different arrangements of particles that can result from, as classified through this Voronoi topology, that can result. And some of you might be a little nervous that for any practical purposes, if we're going to say all 20,000 of these polyhedra are associated with HCP, is that really saying the same as all polyhedra, or almost all all polyhedra with a certain number, up to a certain number of faces? So that leads to the bonus round of, oh wait, did I lose? Okay, yeah. How many? Okay, this is just for those who might be interested. Does anyone have a guess? You could put answers in the chat, or not at all. How many polyhedra, combinatorially speaking, or edge isomorphism speaking, are there with 18 or fewer faces? Okay, because in all the crystal systems we had, at most you end up with 18 faces. It's not true with all crystal systems. Diamond has more, but yeah. So I don't know if. Okay, I can't see everything on the bottom of the chat, but it turns out that there are hundreds of millions or billions. So 20,000 drops in a huge bucket. So there are plenty other polyhedra that are not associated with HCP, for example. Okay. So I just want to finish with 2 things. One, go back to the application that I sort of started off with, and then 2, a few more words about the definitions that I wanted to tell you about before, but couldn't or didn't. Okay, so here's that system we looked at before. Here, we're going to do that same filtering, and on the right side, I'm going to use this Voronoi topology to show the system. So, like if you remember those 6,000 and 20,000 types that I mentioned, we essentially just erased any of the 6,000 of the remaining cells of the 20,000. We colored them all yellow, and then we left everything else. And instead of having this cutting off and this noise, you end up having, I think, a clearer picture. Okay, you don't have as many errors, and I know that's imprecise, and I'll say something about it in a second. Okay, so here's just one more example. I don't know if you can see what's going on here. You probably can't, but the idea is that you have a tetrahedron that has a special structure, and this is a type of defect that appears in copper and in certain materials, depending on what's going on. Essentially, you have some region that has that's sort of off from the lattice by a little bit. It's a tetrahedron. We're cutting it down the middle, so you see a triangle. Okay, and that's what happens. Okay, so the last really 1 minute, and then I'll try to end more or less on time. Goes back to the question of classifying defects. So Oh, oops, that was supposed to be a transition. But I'd mentioned the question earlier. How do we identify defects? But I never really told you what a defect is, and we never had a definition. And the reason I didn't is because there aren't. Every introductory textbook to material science or condensed matter physics has definitions of defects, of a vacancy, a lattice point that's missing an atom, or an interstitial, or a grain boundary. So they have definitions, but not the kind that the mathematicians like. It's not like where it's a precise thing, and we know this because of all these order parameters that are developed. If there's an actual definition, so we would just take that definition, program that into the computer. But there aren't, or there aren't definitions that are applicable to systems that are not at zero temperature, which is great if you're studying a zero temperature system, but not so great if you're studying any system that's not at zero temperature. Okay, so the idea here, and this is sort of like the last idea that I want to leave you with, is that maybe if we use something like the Voronoi topology, or some discrete order parameter, not necessarily that, but I happen to like that, I'm partial, to actually define structure. Like, structure is something that's sort of fuzzy, and mathematics doesn't try to define fuzzy things, but at the same time, it's an integral, basic part of so many parts of sciences that it would be nice to have a precise mathematical formulation of structure. So this is just my point of view, so I'll keep it short, but Voronoi topology sort of gives you the tools for actually defining structure in a rigorous mathematical way. Here's a theorem from 1971 about polyhedra, and about what kind of faces can you have on a polyhedra. Okay, so this seems like nothing to do with what I was talking about, but what's so beautiful if you go back to the language of these tilings is you could convert problems or questions about these sorts of systems into mathematical questions. Here I'll just tell you very briefly. Let me go back to here, and I'm just going to say really one word. And can you see my mouse? Yeah, great. Okay, so here's the mouse, 0, 0, 1, 1, 0, 0, 0, 0, 0, and that 1, 1. Okay, I know you can't see the rest of the paper. Has to do with 5 and 7. And what it says is you can essentially have any arrangement of tiles on the torus if and only if P is different from the sequence 0, 0, 1, 1, 0, 0, 0, blah, blah, blah. Okay, that 1 and 1 corresponds to 5 and 7. And what essentially it says is that in this system, which I use periodic boundaries, that's what you guys call it, torus, we call it torus. And it says that any arrangement of particles that satisfies some conditions is possible, except if there's only 1, 5, and 1, 7. So here, my mouse is near a 5 and a 7. That's what I call a dislocation. And essentially, this theorem tells you that your system can't only have one dislocation if you have these periodic boundaries. Now, material scientists know these things. There's nothing new to them, but they know it. Like we know lots of things, in science. But here, if we sort of transition to the language of tilings and polyhedra and things that we can say exact things about, then at least in theory, it opens up an opportunity to be able to make precise statements. And if you have no other default language to speak about them, then it's open. Okay, so let me just end with a few take-home messages. One is continuous does not always mean useful. Okay, a continuous function. I try to highlight some of its, not just consequent, like not the practical problems, but like the fundamental problems that any continuous function will have. If you're planning on classifying data, doing segmentation, I think you should do it before reducing the dimension. I mean, if you reduce the dimension first using some continuous parameter and then start segmenting it or classifying it, you could end up having you could have problems. And then the last, and this is just something that I believe in, but that this Voronoi topology stuff offers a very natural way of defining and analyzing structure in these spatial point sets as they come up in countless physical problems. All right, I'll stop here. Thank you for listening.
Thank you so much, Menachem. So before we go to questions, everybody could please unmute themselves and applaud. Okay, so if you have a question, you can either raise your hand, the Zoom functionality, or just unmute yourself. Yes, Tzvi.
Hi. So in a lot of the examples you gave, the issue was more of a local, the defect was characterized by this kind of local behavior, like it's different from its neighbors. So in that sense, would it be better to have some kind of a, like the problem with continuity saying like, trying to classify all of the points wouldn't be as important as saying, here are bad points, here are good points. Is there any reason to avoid that approach?
To avoid, can you say the last?
Like just kind of a badness metric.
Oh, sorry. Yeah. So maybe a point that wasn't clear enough before. So like first degree, we want to know where the bad parts are, but also important, we really do want to be able to understand what kind of bad things happen. Do we have what kind of boundaries can appear, and even in many physical systems, the boundary can appear in different ways, and these isolated point-like defects can happen in different ways. So it would be nice. I mean, physicists or computer or material scientists already do these sorts of classifications, but this might offer a way of doing it in a. I mean, maybe the mathematics would be more complicated. You have product spaces that would somehow bridge together these chains or something more complicated. So it might require a little bit more work and more precise than I was able to communicate here. But I think it would be nice to be able to do something like that, if that answers your question.
Okay, do we have another question for Menachem? Actually, maybe I'll quickly ask a question because we're just on that slide. So you see the red and blue alternating here? Is there a, I hate to use the word simple, but is there like a beautiful, maybe elegant mathematical reason why you have to have this alternation?
I don't think there's a mathematical reason in the like combinatorial sense. Via that well, yeah. I think in theorem in theory you could have a bunch of 8-sided things, but I think the physics, and I didn't describe the physics. This is for those physicists. There's a Leonard-Jones potential here that created the system, but in some sense, there's some energy associated with these different defects. The reason that you see so many yellow ones, those are in some sense like local ground states, and the red and blues have different energies. And with a finite amount of energy in the system, there'll be some sort of entropic forces that determine which things appear and how often. And I think, I don't know, that the alternating sequences will in general have a lower energy, whatever that means, than more interesting or less beautiful arrangements. So that's hand waving, as I don't have to say.
Oh, that's a very interesting answer. Thank you.
I had a question. So these 6,000 or 20,000 different sort of polytopes that you can get when you perturb 2 of the lattices, where are those numbers coming from? Is that a computer count or a combinatorial count, or?
So it is a computer combinate. Oops, sorry, wrong direction. So I just want to. Essentially, there's some algebraic equations that describe some instability at the corners. So in the two pictures on the bottom, I actually have these like little red dots on some of the corners of the FCC and HCP crystals, like these little red circles or dark red circles. And those indicate, you can see even points where four edges meet. And there's some instability associated with that. It's some degeneracy in the configurations. And at each one of the corners, there's a certain number of things that can happen. I don't remember, maybe 3 or 4 or 8. And then something, one of these resolutions can occur at each one of these 6 unstable corners. Each of them have 6. And then it's like 8 to the 6th power would be, or 6 to the 8th power, whatever the number is, would be all possibilities. And then there's some repetitions and something. So in theory, at least, it's enumerable what these are, but why there's 6,000 here and 20,000 there, I don't have a good explanation. But those are complete numbers. Exactly.
Thanks.
All right, so I should have maybe said at the very beginning or warned people that I know it's applied algebraic topology, but the focus is more on the applied part and a little bit of topology and probably no algebraic. So